Hi everyone. Today we will have our last lecture, and that will be on deep learning. So we'll continue our discussion on deep learning for computer vision. And this will be on advanced topics. So in the last 4 lectures, we've seen the introduction to neural networks, basics of neural networks, convolutional neural networks. And for the last 2 weeks, I think you've seen quite a number of applications for supervised learning, including segmentation, detection. And this week, we will talk about some advanced topics and applications. And particularly what I prepared for this week is, first, we will talk about the visualization and diagnostics. We will talk about unsupervised localization and classification problem. And lastly, we will talk about unsupervised learning. And that will be discussed in 2 different parts. The first part will be distribution learning. So we will talk about how neural networks can be used to approximate high-dimensional data distributions. And second, we will talk about unsupervised learning of features, which somehow links to unsupervised representation learning. We will start our discussion with the visualization and diagnostic. So far what we've said is that given a neural network, for example, as deep as the one that's shown here, so let me make sure that actually you can see my laser pointer. So let's assume that you have a neural network as deep as the one here. And we've always talked about the fact that this neural network extracts task-specific features. So features that are really optimal for a given task. In this case, we're talking about the inception neural network, and the task there is the recognition of objects in an image. And one question is, so what are these features? Or more generally, how does a neural network work? How does this network able to predict the class assignment so well? So what type of features does it extract? Which areas in the image does it look for the prediction task? And if we can extract such information from the neural networks, our ultimate goal is, can we actually interpret it? Can we interpret how it works? Can we explain how it reaches a certain decision that it reaches? You might ask why these questions are actually interesting. Well, there are quite a bit of domains where understanding a neural network is crucial. To list some of them, we have medicine, we have, sorry about that, so I lost my mouse again. So we have medicine, we have policymaking, the policing, we have applications in law, we have autonomous vehicles, and so on. So in all these applications, critically evaluating the models from a human perspective is crucial. We should be able to ask whether, we should be able to answer whether the predictions of a given neural network make sense. Is the network actually focusing on reasonable aspects of the data? Is this method fair? And can we identify avenues for improvement looking at all these things? So the definition of understanding of interpretation is actually quite vague, and we didn't really specify it. And that definition is extremely crucial. So what do we mean when we say understanding how a neural network works or interpreting how it works? What do we exactly want to get out of the system? And really, there are different approaches with different definitions depending on the task and application. For example, if I'm talking about applications in medicine, for instance, diagnosis in medicine, I might actually be interested in causes of the prediction. I give images to a neural network, and the neural network decides that, well, this person has a certain type of cancer. You might want to ask, so what are the causes for that? What did you look in the image to decide that this person has a cancer? Or if I want to create a neural network that takes images and different information, for example, history of the patient, for example, the person smoked or did not do exercise or this or that, or their diet, the pills that they take, their history of their family, and so on. We might ask the neural network to give us, so what correlations, what relationships caused the diagnosis that I see, caused the predictions of the network. Very related to this, if I'm a scientist, I might be interested in identifying relationships between variables of a complicated system, right? If I'm a risk analyst, I might be actually interested in visualization of the output. So my interpretation of the neural network might actually really mean I want to visualize the prediction and visualize the output in relation to different inputs and really understand and build a mechanism or build a strategy based on these predictions. If I'm actually creating an algorithm for surveillance, or I'm a loan analyst, I'm trying to figure out how much loan should I give to a person so to predict the credit score, then I might be actually interested in interpreting a neural network such that it's fair towards differences in race and gender, right? I might be actually interested in that understanding. I want to understand that neural network actually does not favor certain genders, does not favor certain race, while, for example, assigning credit scores. So it's really the case that understanding a neural network or interpretation is really depending on the task. So let's assume that we focus on a certain task and we basically define what understanding is. And even in this case, it's actually a very challenging task to interpret or understand how a neural network works. Reason? Because given a very deep neural network with multiple layers, there is huge amount of interactions between variables at different layers as well as the input. The information in different areas of the image are used, they interact with each other over and over again in different hierarchy steps. It's a completely nonlinear map that actually goes from the features to the labels. So understanding how the features are used, in what order, how they interact with each other is quite challenging. And we've already talked about this hierarchical mapping. We talked about how actually the entire local statistics are aggregated across the layers and they talk to each other to reach a certain decision. And you can appreciate that just looking back now and trying to understand and trying to dissect how things influence each other and how the interactions play out is very challenging. So we will see one example of, or towards this end. Specifically, we will see how we can visualize the features. Our discussion will be based on a very nice paper from Zeiler and Fergus that was published in 2013. And when we talk about visualizing features, we will specifically focus on one specific definition. We want to visualize the input that activates a certain neuron in a given layer. This will lead us to create what's called a deconvolutional neural network. Okay. So let's start with our general network architecture. On the left-hand side, we have the input image. The input image actually goes through multiple layers, right? And these are all, the red ones are the convolutional layers, followed by rectified linear activations and max pooling. They come to a point where the channel size decreases. I basically vectorize this entire form and create a fully connected layer to yield the final classification. So we're looking at a recognition network. And this is very similar to the one that was proposed in 1998, the first convolutional neural network from Jan LeCun, or the network that actually started the entire revolution in 2012 that actually achieved really good scores in the ImageNet challenge. And so basically the recognition network itself, we will assume that it's trained in the usual softmax manner. So in the final layer, I have a fully connected layer that spits out certain activations in this blue layer, and this blue layer is fed into a softmax layer such that the output can be interpreted as the probability. And I know that if I want to optimize the weights of this network, I simply optimize the loss function given here. Okay, so in this framework, what does it mean to visualize a neural network, to visualize the features? Is I want to interpret features, so I basically really pick a certain neuron in a given layer, and I want to understand what input pattern activates this neuron. So this neuron can be in any of the intermediate layers. It can even be in the fully connected layer. What we're interested in is, so what type of input in this image can activate this neuron? That's what we were interested in. And in a sense, you can imagine that this is exactly the same thing as what does this neuron pay attention in this image? And this neuron can be then used in making the final classification. It's fine. But our interpretation is, how does a neural network work? In this specific example, what input pattern in this image activates this neuron here? So this visualization will be image dependent. The activation level in the neuron actually depends on the input image. And for different inputs, obviously the level of activation in this neuron will be very different. So now, in a very extreme case, assume that my neural network is completely linear. Right? So I take the image and I simply multiply the image with a bit vectorized image first of all, like I have n pixels, so x1 to xn, and I multiply this vector with a big W matrix. And this W matrix, I'm actually interested in, for assume that this is a jth neuron, I'm interested in the activation pattern of the jth neuron. In this case, in a linear map, well, this image, and whatever this image is, it will always be activated, it will always be multiplied by this vector to yield the activation of the jth neuron. And this pattern does not change from image to image. So we can imagine that actually the activation pattern, or what activates the jth neuron, is really this vector that's given here. And notice that this vector is of same size as the image. So this is an image. So it really, I have a single pattern in a linear neural network that looks at the image, tries to identify or tries to look for that pattern, and only if it sees that pattern, it gets activated to a certain extent. And the magnitude of the activation really depends on the magnitude of this dot product. So the WJ row and the X, the vectorized image. And this only happens in a linear neural network. In a nonlinear case, which is the most generic case and the thing that we're actually interested in, things are not that easy. For the general neural network, it's actually quite more complicated than a linear model. The pattern that activates a neuron changes with the input image. We don't have a constant pattern. And why? Because there are nonlinearities in each of these layers. The difference between such a generic neural network and a completely linear neural network is, the activation function and pooling. And these nonlinearities yields a nonlinear activation pattern for this neuron. So the activation here really changes depending on the image. So let me give you a simple example. For two different images, I might see the similar level of activation in this neuron. If I actually look at what pattern that image activates this neuron, they will be very different. And we'll see some examples of this later on. By the way, in these slides, I try to put a lot of information because there's no script for these courses. So it might feel like the slides have too much information, but that's actually to help you study for the exam and help you study the material after the lecture. I hope it helps. So as I said, the difference between a nonlinear network and a linear one are the nonlinear functions. And what nonlinear functions do I have? Well, first of all, I have this nonlinearity that is applied to the activations at each layer. For instance, I have the rectified linear unit that actually, achieves a zero value whenever the activation is smaller than zero and achieves a linear value when the activation is larger. But that's not the only nonlinearity that I use in a given neural network. I actually also have the max pooling. So I take this set of images, and if I want to keep, for instance, one of the largest values, I actually convert this guy into a smaller number of activations like given here. So max pooling is actually quite a strong nonlinear transformation as well. And it's these nonlinear transformations that really gives this nonlinear nature to the network. And as a result, the activation of a neuron really depends on the image. The pattern that activates that neuron changes with the input image. So therefore, the analysis, if I want to visualize the features that this neuron is looking for, I have to do an analysis that really is based on the input image. So I have a new question now, and the question is, in the input image, which pattern calls the activation of a given neuron in an intermediate layer? And this is slightly different than the original question that we asked, which was, which was, as you can remember, what input pattern activates a given neuron in an intermediate image. I had to change it, and now the question that we're interested in is, in the input image, which pattern caused the activation of a given neuron in an intermediate layer? Okay. Now, there are several things that we should discuss. One of them is size of the pattern in the input image changes depending on where, in which layer do I pick the neuron that I want to analyze. Right? Why? Well, we've seen this in the previous lectures. That's because of the receptive field. If I look at a neuron here, the receptive field of that neuron will be large. If I look at a neuron in a previous layer, its receptive field will be smaller. And if I look at a neuron here, its receptive field will be even smaller. So therefore, the activation pattern, so the patterns that activates these neurons will have respective sizes. So this neuron will be activated with a pattern of this size, this neuron with a larger size, and this neuron with the largest pattern here. Okay. Now the idea is we will look at the operations that we do in a forward pass and simply revert them. Now let's assume that we actually focus our attention on a certain two convolutional layers, or like two layers in a convolutional neural network, and the connection between them. So what type of operations goes when we're passing from this layer to the next one? Okay. So what happens? And let me actually focus my attention on this neuron here. So I will basically look at the operations that gives me the activation of this neuron. Well, the first one is I take these activations, or the values in these neurons, and apply a convolution. Right? So I basically apply a set of convolutional filters. And the convolution is followed by a rectified linear unit function, or a nonlinearity in general. And lastly, that's followed by a max pooling. So if I want to actually revert the operations, I have to go backwards. So first, undo max pooling, then undo rectified linear function, then undo convolutions. Okay. So once again, the idea is, when I'm analyzing an image, I simply run the image forward, following these blue arrows. Now, if I want to understand what pattern activates this neuron, what I will do is actually do something very simple. I will keep the activation of this neuron and set all the other ones to 0. Then I will flow this information backwards following the green arrows. And I will explain in detail how this is done. Starting from this layer, I will simply apply each operation in reverse order. Okay? So first, I will unpool. Then I will run through the rectified linear unit again, so rectify the input. Then I will undo convolution with transposed convolution. And effectively, these three operations will give me a neural network that does deconvolution. So effectively, it's a neural network that's linked to this first one, but tries to reverse the operations. And the modified layer, so keeping the activation here fixed, setting all the other ones to 0, will be the input to this modified neural network. So from the paper of Zyler and Fergus, the idea looks like this. This is the forward pass. I simply take a layer, these are the results after pooling. I apply convolution, I apply nonlinearity, I apply max pooling. And when I go backwards, I simply switch to the linked deconvolution network and go backwards. So let's see one by one, how do I actually apply unpooling, rectifying again, and then undoing the convolution operation. First is the max pooling. So the max pooling is actually quite a nonlinear operation, as we said. So we take all these informations, right? For example, these are the neuron values, or like before pooling, these are the activations of a given channel. Now, I will look at each of these 4 areas, and I will only retain the maximum value, setting all of them, ignoring all the rest. So pooling basically simply discards the information here. And you can imagine that unpooling, I cannot regenerate this information, they're gone. The only information that's kept is the maximum activation values, as can be seen here in the pooled map. So pooling leads to information loss. How do I unpool? I do a simple trick. And as I do the pooling mechanism, I basically keep in mind from which locations these maximum values are coming from. So for this guy here, I have a max location switch where I basically keep in mind from which of these pixels the maximum values are coming from. So in the yellow region here, the maximum value is coming from here, so I keep that in mind. In the green region, the maximum value is coming from here, I keep that in mind, and so on. So when I'm actually doing, backward pass, what I do is I use these switch locations with the information coming from top. And the information coming from above can be different from this. Why? Because as we're reverting the operations, most of these operations, as I said, well, I will lose some information. So the information here will not be exactly the same as here when it's coming from subsequent layers. But it's okay. I will use the information coming from above with these max locations, and I will simply place these maximum values in the respective positions. Okay, so this guy will come here. This for the green area, it will come here, and so on. And the rest, I will simply keep the values as zeros. So while I'm pooling, I will place the values coming from above, the layer above, to their respective position that I saved in the max location switch. And I will simply place zero values for all the rest. And you can imagine that the information is lost here. First of all, the information in the max values are not the same. And further, the information in non-max values that were actually discarded while we're going forward are now set to zero. But it's okay. So this is the unpooling operation. The second operation will be, well, I have to revert the rectified linear unit. Now this we can think a little bit. If you think about it, the rectified linear unit, as I go forward, I simply discard all the negative values, right? Instead, I only keep the positive values fixed. So only the positive values actually contribute to the activations in the further layers. So I can actually use just the reverse operation because I already did not use the negative values and they're not useful to activate a neuron. So I don't really have to pay attention to them. So the inverting of the rectified linear unit function simply becomes just applying rectified linear unit again. Okay? So during this reconstruction phase, so during this identifying the pattern, I simply use rectified linear unit as rectified linear unit in the forward and the backward pass. Now, if you had other functions, for example, functions that are invertible, you could also consider using that. You could, for example, if you had a sigmoid function which has a well-defined inverse, you could actually use the inverse of it rather than a rectified linear unit. But with the rectified linear unit, well, if you think about it, the inverse should be the same as forward. Okay, so we did the unpooling and we undid the rectified linear unit with the rectified linear unit again. The last operation was convolutional. So how do we actually undo convolution? And the idea is to use transposed convolution. Now, the transposed convolution will basically, instead of using the kernel, W, I will simply transpose the kernel and apply the convolution. But while I'm applying, I will apply it in a slightly different way. So let's see what it means. In a normal convolution, we've seen this. We've seen that if I had an image like this, for example, 5 by 5, and convolve with an image that's 3 by 3, I simply placed the kernel in all possible valid locations in the image, and multiplied the pixel values with the kernel weights and summed them to get the result for that pixel. And shifted the kernel one by one, first to the right and then to down, to get the result of a 3 by 3 output. Transposed convolution works slightly different. So let's start with an image that's by 3 by 3 and a kernel that's 3 by 3. And our output will be a 5 by 5 image. Here's how it works. Instead of placing the kernel to a location where I can fit it completely, I place the kernel to a location where there is minimal overlap between the kernel and the image. So here there is only one overlap. So in a transposed convolution operation, this is a valid location. What do? I simply multiply the kernel here, kernel weight at this location with the underlying pixel, and sum them up, these guys, they will all be 0, and the result will be the value A, which you can see here. Okay? I will shift the kernel 1 to the right and do the same operation. At this time, kernel weights in these 2 pixels will be multiplied by the underlying pixel intensities, sum them up, and I will get B. And so on, until I go through the first row. And notice that I have 5 values here. Right? So the kernel overlaps with this image at 5 different positions. So I will have this row completed. Then I will do the second row, the third row, and the fifth row. And the transpose convolution will transpose a 3 by 3 image into a 5 by 5 one. And when you think about it, this is not exactly reverting the operation, but somehow changing the size of the image from 3 by 3 back to 5 by 5. So sometimes this operation is also called a deconvolution, but I have to note that this is not the correct terminology. This is simply a transposed convolution. Okay. So I will undo, in a sense, what the convolution did with a transposed convolution. And as the kernel, I will simply use the transpose of the original kernel that I used in the forward pass. So back to this big picture. To complete it, I start, forward pass, and then at some point, depending on the layer and the neuron that I'm interested in, I switch to the backward network and simply undo all the operations until I go to the input. So in this case, the network that they used in the paper from Zaire and Fergus looked something like this. It's quite a small network. If I'm interested in looking at the activation, or like the pattern that activates a neuron here, I simply start going back here until I get an image that's of size, until I go to the input. Okay? And the size of the activation pattern, as I said, will depend on the receptive field of the neuron in a given layer. So let's look at some of the feature maps. What we see here is actually 9 different feature maps that are extracted from the first layer. And these features are actually results of these input images that are given here. Specifically, this feature actually is seen in all of these 9 images. This feature is actually seen result all of these 9 images, and so on. And in the first layer, it looks like, well, the features are kind of not really image dependent, but they really apply to all of them, and that's normal, no? Because in the first layer, I didn't do anything nonlinear. I just simply did a convolution. That's fine. When I go to the second layer, that basically means that I simply applied convolution, rectified linear pooling. Now there's some nonlinearity. That basically means that for each image, a given neuron will have a slightly different activation. So let's see some examples here. Let's look at the neuron that's given by these 9 pixels. So these are the responses of a single neuron in a second layer, and based on these 9 different input images. Now, you can imagine that it looks like this neuron is actually focusing on round structures. For all these images, it actually looks at the round structures and gets activated by these patterns. And let us appreciate the complexity of this. So the neural network is able to, on its own, create a filter that gets activated whenever the input has something round. That's quite impressive. Like this neuron, for instance, these are again the activation of a given neuron in the second layer. And these are the activations based on these maps. So it looks like this neuron gets activated whenever there is a corner in the image. So again, the neural network somehow combined a different set of information so that it creates a neuron that gets activated by corners. And here I have another neural network that gets activated by these curves, successive curves, and so on. Okay, so even in the second layer, I see that actually the neural network creates these neurons that gets activated whenever they see these complex patterns and shapes. So what happens if I go even further into deeper layers? I expect in the deeper layers, the neurons to be activated by even more complicated shapes. And this is exactly what I see. So these are results from the third layer. Now, I basically do exactly the same thing. What I have here is I have one neuron, and for each neuron I have 9 images. And I show the patterns that this neuron gets activated in this image. So you see that, for example, this neuron seems to get excited, seems to be activated whenever it sees regular texture. This neuron seems to get excited, gets activated whenever it sees human faces. This neuron, well, tires. And again, notice the complexity here. The neural network is able to create these neurons, create these extremely complicated feature extractors that gets activated when it sees quite complex patterns in the input image. And notice that the patterns actually are not the same for each image. So the neuron is actually somehow gets activated even when the pattern changes slightly. Even there is nonlinear deformations in the pattern, it still gets activated. So there is some level of invariance to nonlinear deformations and changes in the input image. And this is, again, all due to basically putting the neural network and nonlinearities together. So that's actually quite impressive. This neuron gets activated from all these faces, despite the variation in the background, despite the variation in the action that they're doing, despite the variation of the color of the image and so on. It gets activated when it sees a human face, no matter in what position. That's quite impressive. So one might ask, what happens if I go even further and deeper? I expect, again, even a further level of abstraction, and this is exactly what I see. Here I have a neuron that seems to get activated whenever it sees dog faces. Here I have a neuron that gets activated whenever it sees bird legs. Here I have a neuron that gets activated by these complex water behaviors or interactions between water and objects. Here I have a neuron that gets activated by these corners and so on. When I go even deeper in the fifth layer, I now have like proper object detector almost. Here I have a neuron that gets activated whenever it sees very complicated eyes, animals, a dog face, again, a human face that also somehow gets activated by car tires, and so on. Now, again, let us stop and appreciate the complexity here. So previously, when we talked about feature extraction, we talked about gradients, we talked about combining gradients, we talked about histograms, and so on. Here, we have a neural network, and we're looking at, for example, a given neuron in a given network. And what we see here is we have a feature extractor that gets activated whenever it sees the face of a dog. So it would have been extremely difficult to create such a feature extractor using gradients and trying to combine them using really handcrafted features. And here the neural network is able to identify such a neuron that gets activated by these inputs. So that's kind of the power of neural network. And through visualizing the features that the neurons extract in the network, we're able to appreciate what it does, and we're able to identify what type of features it extracts. So to detect objects, to recognize objects in the images, apparently the neural network has neurons that gets activated by faces of dogs, by more complicated objects, and so on. And with that, I will end this part, and we'll continue next part in the next video.